function g of x is defined on the interval 0 to 8 with the values in the table below. So as you see, this goes up by 1 every time, and this seems to fluctuate just a teensy bit. Based on the table, on which intervals is g of x increasing? All right, well, let's find out what we're dealing with here. So we are looking for when g of x is increasing, and so that happens starting from 0 immediately. It goes from -4 to -3 to -2, and then all of a sudden drops down to -5. So let's just keep this guy going because why not? At -6, we go to -3, so all of a sudden we add again, we add 2 here, and then we drop down again, and then we drop down 1. So it looks like the adding part seems to happen between 0 and 2. Okay, so we'll include 2 there because, that's kind of included. Remember, keep in mind, these little parentheses mean that you don't necessarily include the number. You're just going up to that number. So from 0 to 1.99999 is basically us saying 0 to 2, but don't include 2. And also, where else do we get these pluses? We get these pluses from 4 all the way up to basically 6. So 0 to 2 is one option, and then we'll union it 4 to 6. So we'll go with C as our answer right there, baby. The table below shows the distance d of t in meters of an object over time t in seconds. So we have time t in seconds. We got 10, 13, 19. No pattern, no special order here except that it is in order. And these just go down in some particular non-order either. Doesn't matter. So what we're trying to find is the average rate of change. Now the general formula for average rate of change is f of b minus f of a over b minus a. Obviously in this case we don't have f's, we have d's. So this would be d of b minus d of a over b minus a. A and B are going to be these intervals. Your A, your B. So your A and your B. What would be f of b, or in our case d of b, and what would be f of a or d of a? Well, you would be d of a, and you would be d of b, because this is the result that we get for plugging in a and b respectively. So d of b is 30, minus d of a is 76, all over b, which is 25, minus a, which is 13. So what is that? -46 over 12, which simplifies out to they're both divisible by 2. So -23 over 6. And since this is a rate of change, it's going to be meters per second. So -23 over 6 meters per second, which seems to match up with B. Average rate of change with the table. Different from when you have a function or when you have a graph. It's a little bit friendlier in this case. Just label things, plug stuff in, do a little bit of math, you're set. Which of the following statements is false about the graph on the right? So we want the lie. The double would love that, that's for sure. The function is increasing on the interval -2 to regular 2. Well, increasing means it's just going up and to the right. Just because there's two different types of rates going on here, you have a slope of 1, you have a slope of 3, it looks like, doesn't mean that it's not increasing the whole way. It is increasing the whole way. So this guy is a true statement, which means you are not the option that we want. Let's take a look at B. The average rate of change on the interval 1, 5 is 0. Here's 1, so that lines up with 3. Here's 5, so that also lines up with 3. So average rate of change of 2 points is going to be the slope of those 2 points. Since that's a horizontal line, the slope is 0. You are indeed a true statement, which means I don't want you. Let's take a look at the next one. The rate of change on the interval 2, 6, so here's 2 right here, 2 to 6, is decreasing and constant. Well, let me tell you one thing, it's definitely not constant. The rate of change is not constant, so therefore this is false, this is the lie, so that's the guy that we want. Now the last one, let's just make sure. Instantaneous rate of change means the slope at that moment. We care about where x equals -1. X equals -1 is attached to this red line that has a slope of 1. So the instantaneous rate of change is the slope at that moment. The slope is 1. This is a true statement. So we were good by suggesting that C is our guy. And that's how you do that problem right there. Fun stuff. The table below shows values of a function y for different values of x. So x goes up by 1 every time, y is all over the place. Based on the data in the table, what type of function best describes the relationship between x and y? Well, what we have here in x is this goes up by the same number. So we're talking about equal length input values, right? So since you go up by 1, what I need to do is I need to test what these guys do, and I just simply say, all right, well, if it's linear, then these guys are going to go up by the same number every single time. So let's see if that's the case. Let's see if these guys go up by the same number every time. 2 to 0 is -2. 0 to 0 is 0, so it's definitely not linear. 0 to 2 is 2, 2 to 6 is 4, 6 to 12 is 6, 12 to 20 is 8. So this is not linear because the average rate of change is not constant. So we check to see if it's quadratic by doing the same thing, but with our linear values. To get from -2 to 0, you add 2. To get from 0 to 2, you add 2. 2 to 4, add 2. 4 to 6, add 2. 6 to 8, add 2. Since the average rate of change of the rate of change is a constant number, this is quadratic. So that's going to be our answer. No such thing as both. And neither would be if the quadratic gets you a different number. But since the quadratic gave you a constant 2 every single time, we can say it is quadratic. The table below gives values of the function g of x for selected values of x. So x, you have 0, 2, 4, so those go up by 2 every time, so equal length input value intervals. And g of x is, I don't know, it's a mess. But what we do know is it's quadratic. So what is the value of g of 8? Well, let's see what we could do here. If it's quadratic, okay, we should be able to find the rate of change of the rate of change. I put my arrow backwards. Let's try that again. So if it was linear, we would test this average rate of change by doing this guy right here. So to get from -5 to -1, you add 4. And to get from -1 to 0, you add 1. So which means the quadratic, the average rate of change is going to change by subtracting 3 every time. Okay, so my job is to find out what happens at g of 8. So let's add 2 more spaces to this, 6 and 8. Okay, now what's happening again is I'm going to go backwards here. This guy is going to be -3. This guy is going to be -3. All right, so that would make you going from 1 minus 3 is going to be -2. And you, and that would be from 0 to 6. So let me change that, make it look a little bit better, -2. And in order to subtract 3 again, you would be a change of -5. So 0 minus 2 is going to be -2. I can handle that. And -2 minus 5 is -7. Therefore making our guy -7. Okay, so we kind of did backwardsy looking stuff. And that's how you do it. Fun stuff. Happy times. Name the 2 inflection points on the graph below. Well, an inflection point is where concavity is changed. So it could look like this, where it changes from concave down to concave up, or it could look like this, where it changes from concave up to concave down. Okay, so if I look at this without even looking at my options, we're concave up, and then all of a sudden at B, it switches to concave down. Now this is still concave down, and it might be tempting to say E is an inflection point, but at E, we still keep at concave down. So it's not like there's a change in concavity. There's just like, 2 concave downs next to each other. Change in concavity happens when we are from concave down, then all of a sudden G, we're at concave up again. So B and G are going to be my inflection points, and that's going to be that guy right there. What is the average rate of change of the function f of x equals 3x squared minus 1 on the interval -2, 6? The average rate of change is found by doing f of b minus f of a over b minus a. What's a and b? Well, that's going to be your interval. So I already have my a, I have my b. What I need to do is I need to use this formula to find f of a and f of b. So f of b is me finding f of 6. Okay? And f of 6 is me throwing in 6 into that guy and solving. 3 times 6 squared minus 1 is going to be 3 times 36 minus 1, which is going to be 108 minus 1, which is 107. Now I can find out f of a by doing the same thing, but plugging in -2. So f of -2 is going to be 3 times that's a 4. I was working ahead in my brain. 3 times -2 squared minus 1, which is 3 times +4 minus 1, which is 12 minus 1, which is 11. So f of b was 107, minus f of a was 11. B was 6, minus a was -2. So that's going to get me 96 over 8, which I believe is 12. So C is going to be my answer for that one. Which statement about the function is false? Ooh, I want a false statement. All right, well, let's see what we got here. Y is a quadratic function. The x's go up by 1s every single time, so that's equal length input value intervals. All right, so I don't have to worry too much about that. I have to first find out if it's quadratic, see if it's linear. So in order to find out if it's linear, let's see if these go up or down by the same number every time. So to get from 6 to 0, you subtract 6. Then subtract 4, so it's not linear because those numbers changed already. -2, do nothing, add 2, add 4, and add 6. So it's definitely not linear. Now, it looks pretty quadratic to me because you go like this with the linear numbers to see if it's quadratic. You're finding the average rate of change of the rates of change. So you add 2, 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 you add 2. This is quadratic. This is a true statement, but I want the false one, so I don't want A. Okay? Bada bing. The average rate of change on the interval -2 to 2 is 1. So average rate of change formula is found by doing f of b minus f of a over b minus a. So a and b are going to be the intervals. So you would be my a and b. So if you're going to be my a and you're going to be my b, then you would basically be my f of a and you would basically be my f of b. So in this case, we've got f of b, which is -4, minus f of a, which is nerfing, over b, which is 2, minus -2, and -4 over regular 4 is -1. So we were supposed to get 1. We got -1. This is the lie. This is the lie. Now let's make sure that the other guys are good. Okay. In order to find if something is concave up, what you do is you find out where the rate of change, or if the rate of change is increasing. In other words, if I were to look at the rate of change, all right, I'm looking at my linear values, and my linear values are increasing. I'm going from -6 to -4 to -2 to 0 to 2 to 4 to 6. Those numbers are increasing. Okay, so this is concave up. This was a true statement, which means we didn't want U. And last but not least, let's make sure D is a true statement. The zeros are at -2 and 3, which means if I were to plug in -2, do I get 0? Yup. And if I were to plug in 3, do I get 0? Yup. So the zeros are at -2 and 3. U were true, which means I didn't want U, and B was definitely the guy that I needed. The polynomial function g is given by g of x equals x minus 2 times the quantity 4x minus 2 squared. Which of the following descriptions is true? So they're looking at polynomial degrees and leading coefficients. So this is a shortcut when you have something that's factored out and you're squaring one of those things. I have an x, so I'm going to, and if we're talking about the leading coefficient, we're just talking about the leading terms of each one. So I have an x times a 4x times a 4x. Why two of them? Because it's squared. So x times 4x times 4x really quick is going to be 4 times 4. X times x times x, 16x cubed. Now the rest of this is arbitrary because we only care about the leading term. So this is a polynomial with degree 3, so you are good and you are not. And the leading coefficient is 16, which means you are good. So D is going to be my answer for this one. For the polynomial function h, the rate of change of h is increasing for x is less than 3 and decreasing for x is greater than 3. So the rate of change is increasing, which implies concave up. And then once we hit 3, it changes from the rate of change decreasing, which implies concave down. Now, this happens at 3, so less than 3 is this information, greater than 3 is this information, which means at 3, that happens, we have what's called an inflection point. So we're probably going to be asked about that. The graph of h has a minimum at x equals 3? No. The graph of h has a maximum at x equals 3? No. The graph of h has a point of inflection at x equals 3. Is concave down for x is less than 3? No. And concave up for x is greater than 3? No. The graph of h has a point of inflection at x equals 3? Check. Concave up for x is less than 3? Check. And concave down for x is greater than 3? Check, check, check. Mate. That's how you do that guy right there. For the function p of x equals x minus 7 times the quantity x minus 1 squared, when is p of x less than or equal to 0? All right, well, in order to do this, we have to kind of look at three things. Thing number one, what are our zeros? Thing number two is multiplicity, right? And then thing number three is what does the graph look like by using the leading term? And by there, we can make ourselves a sign table. So my zeros are when these guys are equal to 0. So if I have x minus 7, I have a 0 at 7. And if I have x minus 1, I have a 0 at 1. Now what's important here, so I did that part. What's important here is I notice that my multiplicity for 1 is 2. Now what does that look like graphically? That means as this hits the x-axis, it'll bounce right off. Now what I also notice is my leading term is going to be x times x times x. Now why did I underline this twice? Because that parentheses is being squared. So I have an x times a parentheses times another parentheses, so x, x, and x are going to give me a leading term of positive x cubed, no coefficient, well, invisible 1 coefficient. So this is what this tells me. This is a cubic, or as I like to call it, a Drake cubic, because it starts from the bottom and now it's here. See what I did there? I made a song reference to Drake. I hear he's canceled though. So what I'm going to do is I'm going to make a sign table. I'm going to make a nice little number line right there. I'm going to label my zeros at 1 and 7. Okay, I know that I'm starting down here. So this is, I'm pretending that this is my x-axis. So I'm starting down here. What I also know is as I approach 1, the multiplicity is 2. So if I were to graph this on a regular coordinate plane, I'm going to hit 1 and ricochet right off. I'm going to come back down, and since the multiplicity of this guy is an odd number, I'm going to go through 7. Now my job is to find out where this is less than or equal to 0. In other words, where is this below or touching the line? I'm allowed to touch the line because it's allowed to be or equal to. So starting from the very beginning, starting at negative infinity, I'm already underneath the line. Okay, still underneath it, still underneath it, still underneath it, still underneath it. Right now I'm barely touching the line, but I'm allowed to touch the line. So I'm still underneath it, I'm still good, still underneath, still underneath, still underneath, still underneath. And it takes all the way up until 7 before I realize that I'm going to start being in positive land. Now I'm going to include 7 because at 7 we're at 0 and we're allowed to include 0. So everything else is going to be positive. Everything after 7 to positive infinity is going to be positive above the line, which means everything below the line exists from negative infinity to 7, which is going to be b. For the function p of x is equal to 3 minus 2x times the quantity x plus 2 squared times the quantity x minus 4, for which values of x is p of x less than 0. All right, so we have ourselves a gross-looking polynomial. Whenever you're asked to find out where it's above or below the x-axis, you're looking at 3 things first. Thing number 1 is you need the zeros. Okay? Once you find the zeros, you care about the multiplicity. And then once you figure out the multiplicity, you're going to find yourself your leading term so you know the behavior of the graph. So let's find our zeros first. Our zeros exist whenever each factor is equal to 0. Okay, so my 0 is going to be dependent for this first one on whether it's 3 minus 2x is equal to 0. So you might have to do a little bit of work, subtract 3 from both sides, divide by negative 2, divide by negative 2, and the 0 in this case is going to be positive 3 over 2. The other zeros are really nice. Okay, negative 2 is going to make that 0, positive 4 is going to make that 0. We found our zeros, Chekaruski. Now what we have to do is we have to find the multiplicity of each. The multiplicity of this guy is just 1, nothing fancy there. Okay, the multiplicity of the second one is 2. Now what does that mean graphically? We'll get there in a second. The multiplicity of the third guy is 1, easy peasy. Now the last thing I have to do is find out the leading term. You find out the leading term by taking the leading term of each parentheses and multiplying them to each other as many times as you're supposed to. Now in this case, I'm multiplying this second x twice. Why? Because the parentheses is squared. So my leading term is going to be found by multiplying negative 2x from u times positive x again times positive x a third time, which gives me negative 2x to the fourth. Now what that looks like graphically, and the reason why I do this, is I know this is going to look like an upside down m. Perfect? No. Accurate? Yes. Now what I do with all this information is I make myself a sign graph. I label my zeros, negative 2, 3 over 2, and 4. I'm starting at the bottom here, okay, and I'm going to make sure I notice that as I head towards negative 2, because I know it looks like this, but as I head towards negative 2, since the multiplicity of negative 2 is even, it's not going to go through negative 2. It's going to bounce off like that. Then it's going to come back up. It will go through 3 over 2 because the multiplicity is 1, come back down through 4 for the same exact reasons, and my end behavior goes down that way. So what I'm supposed to do with all this information is I'm supposed to find out when it's less than 0. Less than 0 means don't include 0. So right now, as I'm starting from left to right, I'm less than 0. I am below the x-axis. So everything up to this point right here is less than 0. And then all of a sudden I hit the x-axis. Now when I hit the x-axis, I am 0. I'm not allowed to include 0. So once I hit negative 2, I'm no longer negative. But the moment I keep going, I'm negative again. So I'm not including negative 2. So it sounds weird that I'm saying, let's go to negative 2 and then from negative 2, but that's how it is. So from negative 2 to positive 3 over 2, I'm negative again, right? And then the moment I hit 3 over 2, I'm no longer negative, I'm 0. Now I'm positive, now I'm positive, now I'm positive, but once I hit 4, I'm negative again. And it's going to stay that way forever. So from 4 on is going to be negative. So I go from negative infinity to negative 2, union, negative 2 to 3 over 2, union, 4 to infinity. A is going to be my guy. The function q of x is a polynomial of degree 3. If q of 3 is 0, that means if I plug in 3, which of the following must be true? Well, if I plug in 3, that means I have a factor of x minus 3 living in this polynomial. All right, I know that it's degree 3. it's cubic. So if I have a factor of x minus 3, that means this is going to be some type of quadratic going on in here. Okay, so which of these has to be true? If I plug in -3, I get 0? I don't know, so we can't say that. Q of x has one real 0 and two complex zeros? I don't know. I just know it's quadratic. That could be the case. If I use the quadratic formula on this guy, I could get negative square roots, but I don't know if that's going to happen or not. I can't prove anything, so B's not it. Q of x can be expressed as x minus 3 times P of x, where P of x is a polynomial of degree 2. So C seems to be good. But let's just make sure. Q of x can be expressed as P of x, where P of x is a polynomial of degree 5. I don't know where that came from. That's not even remotely true. I mean, that can't be true. These guys are possibilities, but this guy is definitely not. So C has got to be the only one that will make sense here. So C is going to be my answer. The following polynomial function f is given by f of x equals -7x to the 6th plus 2x squared plus 4. Which of the following statements about the end behavior is true? So in order to figure out the end behavior, we're looking at the leading term. This leading term is not only negative, but it also has a degree of 6, or an even degree. Something that is negative and has a degree of 6 starts from the bottom, does a couple little bumps, and ends at the bottom. Okay, so in this case, the limit as x approaches -infinity, as we're moving to the left without bound, of f of x is going downward, which is -infinity. As I move to the left, I go down, so the limit as x approaches -infinity is -infinity. Similarly, as I move to the right, the limit as x approaches +infinity of f of x, I'm going down again, which means that 2 is -infinity. So the limit as x approaches -infinity is -infinity, check, no, check, no. And the limit as x approaches +infinity is -infinity, check, no, check, no. Wait, hold on. Let's try that again. I tried to be cute here. I don't want to be cute. Check, check, no, no. No, 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 yes. Yes, no. Yes, yes. Well, I hope that helped. Thanks for watching. Given the end behavior of the polynomial p of x in limit notation, I know that p of x is +infinity as the limit approaches +infinity. So the end is going to look like that. N, as the limit approaches -infinity, p of x's end behavior is also -infinity. So I start from the bottom, I end up at top, so kind of like Drake did. And this is only going to happen if first you have an odd degree, and if your leading term is positive. So I need a leading coefficient that's positive, check, and the degree is odd, check. We're at our answer already. Let's just double check. The leading coefficient's negative, nope. It is odd, but still not good enough. The leading coefficient is positive, yup. Even, nope. The leading coefficient is negative, nope. And it's even, nope, nope. So, of course, A right off the bat works, and that's the one that we want. A linear function P is used to model the price in dollars of used trucks as a function of their age T in years. It is known that P of 3 equals $10,200, P of 6 is $6,600. So what this is saying is year 3, truck is worth that much, year 6, truck is worth that much. Based on this model, which of the following is true? Well, it tells me it's linear. So any of this percentage stuff isn't going to be linear, because what you're doing is every year you're taking a percent of the current cost and decreasing it by that much, which means it changes over time. So if you started out at, let's say, $20,000 and you took 25% of that, the car is now valued at $15,000, and 25% of that is different. So it's not going to be any of these percentage ones if it's supposed to be linear. So we need to figure out if this goes down by $1,800 or $1,200. Well, let's do this. If it starts at year 3, if it starts at $10,200, and now it's $6,600, right? And that was from year 3 to year 6, so we'll do 6 minus 3. We could kind of use the average rate of change to see what guide this is going to be. So 10,200 minus 6,600 is going to be 3,600. All that divided by 3 is going to be $1,200. So what you're seeing is this guy goes down by $1,200 every year from year 3 to year 6. Hope this helps. The function f is given by f of x equals 4x squared plus 1. Which of the following statements is true and supports the claim that f is an even function and not an odd function? Well, if something is an even function, what you're supposed to do is plug in negative x to every regular x. And when you do that, you get the original function spat back at you. Okay, so this is the rule for an even function. Now, if you were given an odd function, it would look like this. And I'm going to erase it in a second, but if you were given an odd function, what this means is if you plug in negative x, you get literally the entire opposite thing. That's if it's odd, but that's not what we're doing here. So let me erase that and pretend that that never happened. So what we have to do is we have to take every x value in f of x, plug in negative x, and see if we get the original function. So that's going to be 4 times negative x squared plus 1. 4 times negative x squared is just regular x squared plus 1. And so what we get here is we get the original function that we started out with. So in the same vein, if I were to plug in negative 2, I should get regular 2 if I were to get the original function back. So it's going to be C. So I don't know why I did all this stuff when I could have just looked at what I wrote here in red and got that. But that's all right. I did a little extra, and hopefully it helped a little bit more. Determine which statement describes the following notation. The limit as x approaches infinity of p of x is negative infinity. So we've got some wording here. Increases without bound, decreases. So let's look at this first and then figure out what we have going on. As x approaches infinity means going that way. The p of x approaching infinity means going that way. So the way we would word this, as x increases, okay, as x increases, p of x decreases. So when you see also other words like without bound, that means just forever. So we would word this as x increases, p of x is decreasing without bound. So we need the one that says the graph of the function p decreases. So you're solid so far. You're not, you're good. As x increases is the one that we want. So yeah, this is just a wording problem. This is just vocabulary and stuff like that. But again, this is saying that your graph is going down as x is moving along to the right. So the answer is A. The function f of x equals x minus 2 times x plus 5 times x minus 7 is a cubic polynomial. I see that. How many zeros and local extrema does the function have? Well, this is a regular cubic, and I know it's a regular cubic because it's an x times an x times an x, giving you a leading term of x cubed, no leading coefficient except for the fact that it's positive, which means you are going to look like that. Okay, now these go through 3 separate zeros, no multiplicity. So you go through 2, you go through negative 5, you go through 7. So it has 3 zeros. And if it's a regular old cubic with no weird multiplicity, nothing crazy like that, we're going to have 2 local extrema, a local maximum and a local minimum. Okay, so this has 3 zeros, 2 local extrema. The answer is going to be A. All right, so we didn't have to find out what they were. We didn't have to solve for anything. This is just one of those problems where we have to recognize what's going on and answer the question being given to us. On what intervals is the function decreasing? So we're given this graph, and our job is to find out when the function is decreasing. Well, by definition, the function is decreasing as when you move along the x-axis, you're going down and to the right. It could be a straight line, it could be a wobbly line. All you care about is our graph going down and to the right? Well, here it is going down and to the right and stops doing that at -1. Including -1? No, but at -1. So we can say from negative infinity to -1, our function is decreasing going down and to the right. From -1 to +1, we're increasing, and then from 1, we're going down and to the right again. And it's not consistent, but it doesn't have to be. It's just going down and to the right, down and to the right, down and to the right. So it picks back up from 1 to positive infinity. So we'll say union 1 to positive infinity. That is where our function is decreasing. Now let's take a look at B and understand the difference between what's being asked. B is asking on what interval is the rate of change, not only negative, but decreasing. Rate of change is a fancy word for slope. So it's asking when is the slope negative. That does mean down and to the right, but also if the rate of change is decreasing, that also means concave down. So we need the part where it's going down and to the right and also concave down. So let's see what we marked up here in blue and see if any of this is concave down. And it doesn't look like it is. I mean, this is a possibility, but I'm going to keep going with the fact that this is concave up still, and concave up. It doesn't appear to be concave down until we hit 0, but here's the thing. At 0, our function, or better yet, our rate of change is positive. Here, this appears to be concave down. Okay? It also appears that this guy is concave down. Okay? So I'm going to go with the fact that I'm going to not include 1.5 because 1.5, it kind of seems like it's neither. So what I'm going to do is I'm going to say that it's concave down from 1 to 1.5 union, and then picks back up from 1.5 to infinity. So make sure we understand the difference between the two. The difference between rate of change is decreasing and the function is decreasing. One means that, the other means that. Name the two intervals that have the same positive average rate of change. Now, average rate of change means, slope between 2 points if we're looking at a graph. I want a positive rate of change. Well, that's only going to happen between here and here because that's the only part where I can draw a positive slope. If I were to draw a dot here and a dot here and find the slope here, that goes up to right 1. If I were to do the same thing here and here, that also goes up to right 1. Now the pictures and the curviness of the graph may not be the same, but that doesn't matter here. I only care about the slope. Okay, so it appears to me that between -1 to 0 and 0 to 1, we have the same average rate of change. So I'm going to go with that. So that's our first free response question. Tons of fun. Given the function p of x equals -x times the quantity x minus 4 squared times the quantity x plus 5 cubed, answer the following questions. So we have this polynomial here in factored form. We got a negative out in front. We got 1x living out there. We've got 2x's living in here. We got 3x's living in here. Okay. State the zeros and the multiplicity of each. So part 1 is not so bad. You take a look at each factor and you would say, all right, well, the number that would make -x become 0 is just 0. Easy peasy. The number that would make x minus 4 0 would be 4, and the number that would make x plus 5 0 would be -5. Okay, so those are my 3 zeros. So my zeros are x equals 0, 4, and -5. Now the multiplicity for each, is completely dependent on how many exponents are attached to that factor. -x has an invisible exponent of 1, which means the multiplicity is 1. 4 has a multiplicity of 2 because of its exponent, and -5 has a multiplicity of 3 because of its exponent. Okay? So there you have it. There's our multiplicity. There are our zeros. Now we can use this information, plus a little bit more, to answer B. B wants us to find out where p of x is positive. So this is what I need to do. I'm going to draw myself a simple sine graph. I'm going to mark my zeros, which were -5, 0, and 4. I need to find out what my zeros are. Check. I need to find out what the multiplicity is. Check. But what I also need to do is find out the behavior of the graph. And the way I do that is I use the fact that I underlined these x's. I underlined a negative x. I underlined two x's here, right? Because there's two x's. It would be x minus 4 and x minus 4. So I'm going to multiply x squared. And I underlined three x's here, so I'm going to multiply x cubed. Now, by underlining and multiplying the leading terms of each factor, I am finding out what type of graph this is. Negative x times x squared times x cubed is negative x to the 6th power. That is an upside down, I guess, is it sextic? I don't know. Looks like that. That's all I know. Now, this is what I also know. Since I know the multiplicity for 4 is 2, it's going to bounce off of 4. So as I start writing this out, as I start drawing this out, okay, it starts from the bottom like Drake does. It's going to go through negative 5 because it has an odd multiplicity. So it's going to go through negative 5. It's going to come back up, maybe do a wobble here and there, but who cares? Go back down and go through 1 because it has a multiplicity of 1. But when it comes up through 4, okay, it's going to bounce off of 4 because of that even multiplicity. Now, somewhere up here or down here, we have more bumps, but that's not my concern right now. If you want me to put a bump there, go ahead. That's not my concern. My concern is where is this positive? And it's positive at one spot, and it's that interval right there, from negative 5 to 0. Now, do we include negative 5 in 0? No, because we only want it to be greater than 0 and not greater than or equal to. So we want the spots that are only greater than the x-axis, only above the x-axis and not touching it. So we will say negative 5 but not including, all the way to 0 but not including, and that's it. Now, if we did include 0, then we would put brackets here, and we would also include 4. But we don't have to do any of that because we only care about when it's above the x-axis and not when it's touching. Now, last but not least, we are going to be asked to write out the end behavior in limit notation. We know what the graph looks like. We know it looks like that, which means we know that as x decreases, my graph goes to negative infinity. So how do we write that out as limit notation? The limit as x approaches negative infinity of p of x is also negative infinity. As my graph goes to the left, it goes down. Similarly, as my graph goes to the right, it also goes down. So we would say the limit as x approaches positive infinity of p of x is also negative infinity. Okay, so that's free response question number 2, all about polynomials, baby.